Hello, everyone. This is Mingxi Wu. I'm VP of Engineering of Tiger Graph. Welcome to Graph+AI 2022. Today, I'm going to share with you Tiger Graph's results of implementing Ldbc social network benchmark business intelligence workload. So before I start, I'm going to introduce Ldbc. Its full name is the Link Data Benchmark Council. So this Ldbc organization is a nonprofit organization whose mission is to define standard graph benchmarks. Ldbc consists of members from both industry and academia. And the industry vendor is mostly the graph database vendors, and Tiger Graph, Oracle, Polymetry, and Graph and Group, and so on. And this organization is established in 2012, and its main mission is to design a particular benchmark workload, and so that the different graph database vendors can implement and compare their performance against each other. I'm going to talk about the one benchmark in this organization, and this benchmark's name is Ldbc Social Network Benchmark. I'm sometimes call it SNB benchmark. And this benchmark has two workloads. And the first workload is interactive workload, and it targets short queries, and you can think it as OLTP workload as in the RDBMS, relation database management system context. The second workload is business intelligence. You can think it as OLAP workload corresponding to RDBMS. In the interactive workload, most of the queries are 2 to 3 hop neighborhood queries with filtering. And in the business intelligence workload, the queries are more complex, and it targets multi-hop, and including path queries, including subgraph queries with filtering and aggregation. And in order to pass the audit for the interactive workload, you need to run your benchmark, run the benchmark against the 30 gig, 100 gig, and 300 gig data sites. For the BI workload, you need to benchmark against 100 gig up to 36 terabytes, depending on your database scalability. And it can continue to 100 terabytes, and it's still ongoing. And the Ldbc task force is working on generating 100 terabytes data for interested vendors. And for the interactive workload, and it includes mutation commands, such as inserting new vertex. And for the business intelligence workload, it includes micro batch update workloads, which targets to mutating the graph with insertion of edges, vertices, and deletion of edges and vertices. And some of the deletion is cascading. So if you delete a vertex, the connected edges and vertices are cascading and deleted. For the interactive workload, the target benchmark metric is throughput. So it measures how many queries you can answer within 1 second. For the business intelligence workloads, the targeted metrics is the mean latency of the 20 BI queries. So now let's take a closer look of the BI workload. So as I said in the previous slides, the BI workloads are designed to measure your database capability to handle OLAP style queries. And it also simulate the real life situation. So on the top right of this slide, it shows how a real life OLAP system are set up. So you may have an OLTP database, and it accepts transaction queries. And sometimes you want to run analytic queries. And the OLTP database system can generate the transaction logs, which record the insertion deletion transactions that feed into the OLTP database. And also you can dump the entire database to an initial snapshot. So this blue box indicates that you dump the OLTP entire snapshot, and then it goes through data cleaner and aggregator, and then generate the initial snapshot of the database. And the transaction log record all the insertion and deletion commands. And after the transformation, you generate a list of statements of insertion and deletion of your database. And the analytic database system is your graph database. You can load the initial snapshot of the database and then incrementally mutate your graph by the insertion and delete commands while you are benchmarking a set of well-designed queries on your system while you're mutating them with the insertion and deletion. So as I said, the benchmark includes initial load, batch updates, and then a set of well-designed queries to test your database performance. And particularly, I want to point out those queries in this benchmark suite are very complex operations. And usually they touch a large amount of data. And Ldbc SMB benchmark have auditing rules that specify how you are going to pass the auditing rules. And on this slide, the bottom right, it shows the graphic representation of how BI driver looks like. The BI driver is designed for each a specification is designed for each vendor to implement so that it can pass the Ldbc BI benchmark test. I'm going to do a deep dive of how the driver look like. The top part of this driver includes a data set generation and batch insertion and deletion generation. So it starts from a graph raw data generator. It can generate a temporal graph. Temporal graph means the graph elements, some of the graph elements has timestamp. And while you generate the temporal graph, this temporal graph are forked into two batches. The first batch are used to generating those macro updates. So you can see the batch splitter will take temporal graph as input and then generate batch update 1 and then up to batch update 33. And each batch consists of a set of insertion and deletion of the graph. And also, the temporal graph feed into the graph serializer. And this graph serializer will generate the initial snapshot of your graph database so that you can load into your graph database in bulk and then have an initial state for your graph database to start. And you can see that the initial graph snapshot are loaded into the graph database where the benchmark driver using the load commands. And then subsequently, the benchmark driver allow the auditing to invoke batch update 1 and then up to batch update 33 in sequence. Let's take a look how the query parameter are generated. After the temporal graph is generated, it feeds into a module called the parameter generator. And this parameter generator goal is to generate different parameters corresponding to the graph state so that you can invoke the BI queries with these parameters, and it guarantees your query will return non-empty results. And this parameter generator generates a set of substitute parameters, and it corresponding to each batches. After each batches macro batches update. So for example, this substitution parameters will generate for batch 1 queries. After batch 1 is is invoked to mutate your graph, you can use parameter 1 to invoke BI query 1, and parameter 2a, P2a to invoke query BI2, and parameter P2b to invoke query BI2, and so on. Some queries you have multiple parameters, some query you only have one parameters. And you do the same for other batch updates. So the parameter generated corresponding to the batch update, so that they can test whether your query can see those updates after the database is mutated. And I think that is a brief introduction of how the benchmark driver and the benchmark process look like. Now let's take a further look of how takeograph results look like. And before I go to the query results, I'm going to briefly describe the social network benchmark schema. So this schema is used to simulate a real-life social forum scenario. So the main entity in this social network schema contains a forum. Person can post a message in the forum, and the forum has member of different persons. So person belongs to a forum. They can join other forum as well, and each forum has a moderator. It also pointing to a particular person. And each forum is a container of a set of posts and a subsequent comments of the posts. And the posts and comments are subclass of the message. So you can say post is a message and the comment is a message. And also there are demographic information of a person, such as the person work at a company, and the person studied at which university, and the person is located in which city. And we use tag entity to provide taxonomy of forum and the messages. And person can show a particular interest in a particular tag. And also we have a geolocation entity to associate with a message. So the comments or the posts are coming from a particular country. And based on the properties of different entity, we divide them further into dynamic entities and static entities. Dynamic entities means those entities that will evolve over time. So for example, initially I have 1,000 person, and then I mutate the graph database with a new set of person. And with the time dimension evolve, I have seen the person community keep changing. The same thing happens for the forum. I initially have 10 forums, and with the time elapsed, I may have 20 forums or 5 forums based on the insertion and deletion of the batch updates. And also posts and comments is also evolved with the time. That's why we call those entities dynamic. Their cardinality are changing with the time dimension. We also have static entities in this graph. And this set of entities are fixed, and it's a set of fixed entities that associate with each scale factors. So for example, you have certain number of universities, you have certain number of cities, and you have certain number of tags and the tag classes, etc. So here I'm going to show the magnitude of the scale factor 10,000. At the scale factor 10,000, after we generate the raw graph, it consists of 23 billion vertices and 173 billion edges. And this table breaks down the cardinality of each entities and some typical edges. The reply of edges in scale factor 100 has 185 million cardinality. And at scale factor 10,000, you have 18 billion edges. And roughly, you can think about 100 scale factor 100 will generate the raw data about 100 gigabytes. And scale factor 10,000 will generate about the raw data 10 terabytes. And Telegraph implement the official Ldbc SMB benchmark driver, and it has been included in the Ldbc official GitHub repository. So you can access them here for the interactive driver, and you can access the BI benchmark driver here. And both driver has been validated, cross-validated with other products. For example, the SMB interactive driver has been cross-validated the results with Neo4j at scale factor 1. And the Ldbc SMB BI driver has been cross-validated with Umbra at scale factor 0.1. And we tried the largest attempt for the Ldbc SMB BI workload. We have successfully attempted the loading at the 36 terabytes, which is 30K scale factor. And I'm going to present the loading speed for Telegraph. So for this experiment, we use Telegraph 3.6 release candidate, and we tested our loading speed with this 36 terabytes benchmark data. The loading take up to 246 gig per hour per machine. And we use 40 GCP machines, and each with 128 CPU, 864 gig memory. The end-to-end loading time is 3.75 hours for 36 terabytes on 40 GCP machines. And after the loading, we check the footprint of the disk. Each machine is occupied by 454 gigabytes of the graph data. And if you calculate the compression, we achieve the compression ratio of 2.04. Here are some insights that during our experiments, we conclude. So currently we notice the data generator generates many small files. And if you use those small files directly, small files, we define those file size is less than 2 gigabytes. Or some graph hub nodes in the data. Both factors will trigger a slow loading. And if we don't do any pre-processing, the loading will arrive at 40 gig per hour per machine. And how we solve this slow loading problem? So first, we pre-processing those small files. We combine those small files into big files and load the big files. This will dramatically improve our pipeline loading and improve the loading speed. The second trick that we did to eliminate hub nodes is by a clever schema design. And when we see some nodes have too many edges, outgoing edges or incoming edges, and we try to avoid that by materialize those edges as attributes of their target entity. And this design will help us to eliminate those hub nodes during the loading. So with this two technique of processing strategy, we can improve the loading per hour per machine from 40 to 246. And that's how we obtain the 3.75 hour end-to-end loading of 36 terabytes on 40 GCP machine. And now I'm going to present our end-to-end solution of implementing the BI query workload in scale factor 10K. So the setup is 16 GCP machine. And again, we use Telegraph 3.6 release candidate. And the machine has 128 vCPUs. Each machine has 864 gig memory and attached with 4 terabytes SSD persistent disk. The operating system we used is CentOS 7, and here is the Linux kernel version. With these 16 machines, we run the complete benchmark following the benchmark driver specification strictly. And I'm going to present the results in subsequent slides. So here is the query performance of Tiger Graph 3.6 release candidate at scale factor 10,000. Each box represents one query, and the BI query workload consists of 20 BI queries from query 1 to query 20. And some queries require 2 parameter input. For example, query 2 require parameter 0 to A. That's one set of parameter for query 2. The second set of parameters is 0 to B. And there are other queries that require 2 parameters. For example, query 8, you have 2 set of parameters, 0.8, 08A and 08B. And also query 14, query 15, and 16. And for each query, we conducted 10 runs using different parameters at a different time points, because when we run this BI benchmark queries, it will require you to do batch update 1, and then you run the 20 queries with a set of parameters, and then you run batch update 2, and then you run the 20 BI queries with another set of parameters, and then you repeat this 33 times. So for the BI query 1, we record all the 10 runs at different time points, and the y-axis is the absolute time in seconds, and we plot them. So for example, one invocation of BI query 1 takes 7.25 seconds, and another invocation of BI query 1 takes 6.75 seconds. We noticed there are some expensive queries. For example, BI 6, it takes 1,200 seconds, more than 1,200 seconds. Some runs takes 1,100 seconds. And the difference is because they are invoked at different time of the database state. And sometimes you have more graph elements after the batch update, then you may take more time to run. And sometimes due to deletion or initial state, you may not have that many graph elements, and you take less time. And then we plot them here. And here I list the semantic description of each BI queries. And you can find the details of each query from the Ldbc benchmark official documentation. So some query highlights. And after we run this benchmark, we noticed that Telegraph can run the shortest path algorithm, can run those queries that involve shortest path algorithm only take several seconds. For example, the query 19 and query 20 both include shortest path algorithm in the query pattern. And most of the BI queries, Telegraph can finish them within 1 minute for all the 10 runs. And this is significant. Consider this is a distributed graph database processing 10 terabytes data, and with complex query pattern, and which touch majority of the graph elements in this graph. So to give us a flavor of how complex the query could be, so here is the BI 17 picture pattern. So this query is titled Information Propagation Analysis. Its input is one person and one message, and this person create a message in create a post in a particular forum, and two other person 2 and person 3 also belongs to this forum. We assume they see these posts, and we want to find is person 2 and person 3 discuss this post in another forum. And how do we find that? We use the message tag, and use this tag, one hop and two hop, find the message of similar tag in the second forum. And the second forum must have a condition that person one does not belong to the second forum, so that the person one does not know person two and person three are discussing her topic in forum two. And then we find person two and person three in forum two, and their discussions about a post. And this post must have same tag as the initial message that person one posts on the forum one. And the query asks what are the distinct message in the thread of discussion of this particular post of the same tag. So you can see this is the multi-hop and with cross product of another forum, and then do a group by, and then do dedupe distinct count, and then return the final results. And we can finish this BI 17 query at a scale 10 terabytes within 30 seconds. That's all I'm going to present today, and hope this gave you a concrete idea what's the capability of Tiger Graph enterprise version, and which can handle distributed query at scale 10 terabytes with 16 machine, and strictly follow the Ldbc SMB benchmark auditing rules. And we are proud of this achievement, and I hope everyone will have their hands on to try our product to solve real life problem. Thank you.